Thanks. I'll begin with a word of prayer. So, excuse me. Heavenly Father, we thank you for this day. Thank you for the students. I just pray that you bless this class and help us to use this time, Lord, for your glory. In your name I pray, Lord Jesus. Amen. One of you, excuse me, I'm actually better, believe it or not. I know it doesn't sound like it, but I'm getting better. One of you mentioned that I'd solved a different problem in the homework solution than was in the solution. Yeah. Which problem was that? Which one would you like me to solve?
The one that I have is 7.7, question 36.
7.7, number 36. I hope I can do it. Let's see here. Yes, this is a good problem for us to do. So here we're faced with the integral of dx over a squared plus x plus b quantity squared. Right? So this is section 7.7, number 36. Now this is not an integration by parts problem. This is just something related to basic inverse trig problems, right? Okay, so how do we do this? Basically the idea, there's different ways to do it. Here's what I would do at this point for you guys. I might do it a different way if you ask me in a week. If I factor an a squared out, this is 1 plus what? X plus b over quantity a squared, right? And so that suggests to me I can make a u equals x plus b over a substitution, right? So if I do that, what's dx? So du is equal to what? 1 over a times dx, right? So make the u substitution. We've got a du divided by a squared times 1 plus u squared. So I need the talking to stop, guys. So what do we got here? We got 1 over a. The integral of du over 1 plus u squared, which is what? Remember, inverse tangent plus a constant. And so what do we have? So that's how you do that one. So I solved something different in the solution? Like a similar problem, but different?
You solved the one above it.
Ah, okay. That sounds like that sounds like something I might do. So do you guys have other questions about homework?
Yes.
Go for it.
In 8.2, 34, I did not know what to do with the dv. Like had it.
Oh, great. Cosine, let's work out the example, cosine root x. Okay. The integral of the cosine of the square root of x dx. Now we could do sine square root of x. It'd be pretty much the same animal, right? Let's do this one. I think we should let u equal to all of this. And we should let this be dv. Let's see if that works for us. If u equals to the cosine of the square root, then du is what? Minus the sine of the square root of x, right? Divided by 2 times the square root of x. Why do I divide by 2 square root of x? The derivative of the square root function is 1 over twice the square root function. It's the chain rule. So, all right, I've left myself not enough room here, sorry. uv minus the integral of v du. and then poor planning on my part. Sorry about that. Oh, so dv was what?
It said dv was equal to cosine x squared. X squared over x squared. dx. Square root of x. That's what I meant. Square root of x.
You're going off some hint in the book or something?
Yeah, it said.
Oh, forgive me. I'm ignoring the hint.
Okay.
Yeah, much to my own peril, right? Yeah. Well.
U equals.
Well, I mean, let's just bear with me here for a second here. We'll see why not to do this. As I was telling you guys last time, at some point I will show you an example of what doesn't work as a point of pedagogy. That time is now. Of course, this is something I planned. Being a mentalist and all, I forced you to ask me about this question. And let's see, here's the integral of x. Oh yeah, you see this is going nowhere fast. X sine to the square root of x over 2 square root of x du. It's like, oh no. Well, to quote my community college professor, this dog does not hunt. So we should try something else. A kind and benevolent book has given us a suggestion which I have ignored, which is what? We should try to make u equal the root x. So instead we'll make u. So I think this is a good example of some place where I'm not so sure Liate really reigns supreme, eh? Does Liate tell you to make u equal square root of x? I don't know, maybe it does. Log, inverse, that's algebraic. I guess Liate wins. I should have, if I had been listening to the Liate, or the Ilate, as some of you told me, I would have noticed that a comes before t, and I would have, oh well, it's too late. Anyway, so if u is square root of x, then what?
T is 1/2 x.
Yeah. That's fine. And then they tell us, because they're nice, that dv is what?
Cosine square root of x over square root of x.
Dx, I suppose. So the point is, you have to kind of start with the original problem, right? If you tilt your head and squint, you go, hold on a second. I think that there is a how to do this. Cosine square root of x. So this says what? Dx is equal to what?
What? Probably like.
What? Wait a minute.
I don't know.
I don't know how
Oh,
to
I'm
do
sorry.
that.
Well, that's the hint, so we deal with it. V, though, is what? I'm sorry, integrate that. What is V? How can you integrate that? That's why I'm having trouble.
Put it next to
There's a couple questions. First of all, this is allegedly UDV, right? So what's the U and what's the V?
the U is this.
U is square root of x. So this is allegedly equal to the square root of x times dv, which was apparently cosine of the square root of x over the square root of x dx. Well, okay. You see? Oh, yeah, look, I just obviously need to divide and multiply by root x. The reason this is reasonable is because you were given a hint. Without that hint, this is probably not reasonable, but you were given the hint. The question, though, then, great, so it applies. This is, in fact, UDV, but what's V? Because we need to figure that out in order to do the next step, right? Can you guys, what's the integral of cosine, right? We have to integrate cosine root x over root x dx, which is what? I'll make a w substitution. This is the integral. Let w equal the square root of x, right? So dw is equal to 1 over 2 square root of x dx. So you see that's really what? 2 cosine of w dw? Right? And so this is really 2 sine of the square root of x. Excuse me. So the point is v is twice the sine of the square root of x. And there we go. So we've got 2 square root of x, that's my u, sine square root of x minus the integral, excuse me, 2 sine square root of x, what was my du? Du is what? It is dx over 2 square root of x, right? So let me clean this up a little bit. What do we have? We have 2 square root of x, the sine of the square root of x, right? Minus the integral of the sine of the square root of x dx over what? Over root x. Oh, but that's not too bad. We know how to do that integral, right? We just let w equal square root of x, and what does that give us? Sorry, I was thinking this is one of the ones that's loopy, but this isn't the one that's loopy. This is the this is just a w substitution, excuse me. Right, making the same w equal root x substitution again, and then what do we have?
Wait, where's that 2? Oh, I see.
And there you have it. I went ahead and did I plugged in w equal root x as I did the integral because I ran out of board. But I will agree, when I first saw this hint, it took me a minute or two to wrap my head around it. Like, what do they mean dv is that? That's not a dv that's sitting there, right? You got to use your imagination to see that there is that dv, but you have to invent it in order to put it. I mean, you have to kind of make it happen. So, this is certainly a harder problem. If you take the hint away, this is a more sophisticated problem than most of the ones that you're assigned and we've looked at so far, right? Any other questions about homework before I go on? Okay. Let's see here. How about the integral of the log of x? Yeah? Oh, stretching. That's cool. Integral of log of x quantity squared dx. How would we do this one? I'm sorry if this is one I had signed. I just picked it out at random. It may be one of the ones that I recommended. I don't remember.
I don't think so.
No? Okay, cool. Let's see here. If we trust Liate, we will let u equal log x, right? So then du will be dx over x. And so, oh, log x squared, right? Sorry. So that's not what du is. Du is 2 log x divided by x times dx, right? How do I know that? Chain rule, yeah. And then what my dv, if this works. So dv equals dx, so v equals x. So what's it get us? This gets us x ln of x quantity squared minus the integral of x times 2 ln x over x dx. Simplify that a little bit. Hey, look at that. That brings us back to the integral of log x, which we did yesterday, right? How do you do integral of log x? Integration by parts, right? Do you guys remember what the answer was? Yeah, this one was x ln x minus x. We worked that out yesterday, so let's just use that since we used it. Since we just worked it out yesterday, let's not go over it again. Let's just use it. So minus 2x ln x plus 2x plus a constant. Using yesterday's work. What's that?
You said the natural log of x contributed to 1 over x.
Oh, no. The integral of dx over x is equal to the natural log of the absolute value of x plus a constant. But that's a very good question. Because that's a confusion that we want to, like, get rid of, you know? Now, I don't know about you, but if somebody asked me, okay, tell me a function that when you differentiate it, you get back the natural log of x quantity squared, I personally can't just go, I know, it's x times the log x squared minus 2x times the log x plus 2x plus a constant. If you differentiate this, you get that. That is far from obvious, right? It's pretty cool how we can kind of build our way to these sorts of backwards derivatives, right? What if you were asked to integrate the sine of the log of x dx? Let's see here. So I think what I'm going to do is I'm going to let this be u, and I'm going to let this be dv, and see where that takes us. Right? So I'm going to get x sine of the log of x minus the integral of, all right, fine, I'll write my work over here. Du is what? So like this x and that x cancels, right? So what you're left with here is the cosine of the log of x dx. This is, of course, uv, and this, of course, is v du. All right? I love how those x's cancel. So neat. You're like, you just replaced one problem I can't do with another problem I can't do. So what good is that, right? I mean, surely cosine log x is just as hopeless as sine log x, right? But if you get enough hopeless people together, you can do something, right? Oh, I'm sorry. Yes?
How did you know like what to pick for U and DV?
Yeah, I know, right? I don't know. I guessed. Like I said, you make a choice.
So you just guessed.
You guess, yeah.
I like how I kind of like learned it when I first was introduced to this kind of stuff.
Uh-huh.
I always go with the most complicated part of you.
Yeah, most complicated part, make it u. Usually works, except when it doesn't. Like
Oh, yeah.
here, there's no universal answer. I mean, it's practice. But the Liate is usually a pretty good guide, although it seems to let us down here, unless you understand Liate more deeply than I do. I didn't pick the log, did I? I did not. Although it hasn't been shown that this is helpful yet, has it? Go ahead.
Well, I was just gonna say, so like, there's ones where you have like hours like super high. There's just no better way that you learn to.
Oh, I know a better way. I'll show you a better way in a second, yeah.
Oh.
I do not teach this table method because I think it's just stupid. But there is some fast table method, but if you write that, I don't know how to grade it. So unless you have the right answer, I'll take off all the points. Sorry. But, you know, I only grade methods I teach. If you use some other completely different method, well, you better get the right answer. Yes. Oh, no, okay. So here's what we're going to do. We're going to make this u2, and I'm going to make this dv2. And so that's going to give me minus x cosine of the log x. Minus minus gives me a plus, the integral of, oh, stink. I better Fine, parentheses are our friends. Let me use them. Parentheses, parentheses, same parentheses, all right? Minus the integral. So here, u2 is cosine log x, right? That makes du2 minus, notice that minus, sine of log x over x dx. So that gives me a minus sine of log x dx. The x's cancel, right? This x and the dv2 equals to dx gives me v2 equals to x again. So like the 1 over x from the du2 and the x cancel. But how many minus signs total do you got? Count them. Uno, dos, tres. Let's see here. X sine, that's about all I know in Spanish. Let's see here, sine x minus x cosine log x, and then minus the integral of the sine of the log x dx again. You're like, so how is that helpful? Right? We just got back where we started again, right? Add the integral. I think combine them. Yes, you are on the right path. See, what I said is not entirely truthful. We didn't get back where we started. We go back to minus what we started, plus some junk, right? If we had actually gotten back to exactly what we started again, that probably would have been a bad thing. But this, if we call this I, right? Because that's what we're after, the integral I, then this is exactly minus I, right? So if we add I to both sides, this gives us twice I equals x sine of the log of x minus x cosine of the log of x. And then from this we learn I is equal to 1/2 x times sine log x minus the cosine of log x. And then of course this is an indefinite integral that we're doing, so I add a constant for good measure. And there you go. I call this phenomena looping. It loops back to where it started. I don't think it's just me, but cool, huh? Yep.
I actually have a question about something that I noticed that you do on your
Go for it.
the end of your equations and whatnot. When you figure out on your solution, you do a line and put a dot.
Mm-hmm.
Is that like period supposed to denote like the end of the problem, or is it?
Yeah. Well, I have two things I tend to do. The one is to put a box around the answer. The other is when I'm writing solutions, if I don't feel like writing boxes, I will underline it and put a dot, which says that's the end of it and that's the answer. Yeah. I usually ask you guys to box answers on tests because otherwise I don't ever know where to look, especially with some of you. I try not to take off too many points just for formatting, but I am. My ability to not be petty only goes so far. I don't know. Okay, so anyway, how about this one? You're like, oh, this is the same as this. So we'll just integrate by parts twice, right? In a loop. Why is that the wrong way to do this one? Because it's a cinch. It is a cinch, in fact. Here it is. See, I like you guys, so I showed you this before I gave you the test. This, of course, is not an integration by parts problem. Right? Yeah. Yep.
Does, like, our cinches, Kosh, and Yate, are they part of the tree?
Oh, that's a good question. Where do cinch and kosh fit into liate? I have no idea. That's an interesting question. I don't really know. Of course, I'm just using this here, right? The definition of cinch as we talked about last time, but I mean, not last time, but the other time. I don't know. I mean, certainly if I have something like the integral of x times the cosh of x, I can do integration by parts on that. You know, like this one, for example, I would that would make that be dv, I'd make this be my u. I know that's how that's going to go. Let's work through this one. That's actually a very interesting question. I'm not sure what to say to that, generally. So I'd say, let's see, I'd let u equal x. My dv was cosh x dx. Again, you know, the liate is just a heuristic. It's really not a universal truth. It's just something to try. If it doesn't work, try something else, right? I think Eliot said it best. Dust yourself off. Try again. Let's see here. If first you don't succeed. Let's see here. And then what do we do? V du, right? So uv minus v du. So in this case, it's cinch dx. And so there you have it. So this is a lot like one of my first examples. Didn't I do x sine x last time? Did I? I might have. I don't know. Let me show you another one that loops. Okay. How about this? The integral of e to the 3x times the cosine of 2x dx. I will regret putting the 2 and 3 there, but I'm doing it to show you the difficulty, all right? Again, I may regret it. Okie doke. So what do we do? Actually, here, I don't know. Like, I think you can either go... I think there are two right choices here, and I think they'll both do the same thing. So I'm just going to make a choice and show how it works, but I don't think this is the only path. So let's say if we make this my dv, and if I make this my u, let me say 1 and 1. So u equals to e to the 3x u1. Then du1 is 3 e to the 3x dx, right? And my dv1 being cosine of 2x dx, that makes v1 equals to 1/2 sine of 2x. So, okay, so I've got u1, v1, right, which is 1/2 e to the 3x sine of 2x minus the integral. v1 du1, so that's 1/2 sine 2x times 3 e to the 3x dx. All right. I'll clean that up just a bit before I go on. So I've got 1/2 e to the 3x, the sine of 2x, minus 3/2 the integral of the sine. Let me write it in the same way I did before. I'll write the e to the 3x first. E to the 3x, the sine of 2x dx. Parentheses are your friends. You should use them. They will help you if you pay attention to them. So I'm going to put parentheses here. I'm going to apply integration by parts the second time inside those parentheses. So what's my my u2 and my v2 going to be? Yeah, right. Basically the same thing, but with sine. Indeedly doodly. See here. So this will be my dv2. This will be my u2. So that gives us du2 equal to 3x e to, 3 e to the 3x dx. And that gives me v2 equal to minus 1/2 cosine of 2x, because the integral of sine is minus cosine. The half because it's a u substitution. The argument's not x, the argument's 2x. I have to divide by 2. So, all right, this gives us so what I need here is I need u2 v2, which is minus 1/2 e to the 3x cosine of 2x, all right, minus the integral of v2, which is minus 1/2 cosine of 2x, du2, which is 3 e to the 3x dx. Close my parentheses. All right. Now we're almost, see, oh look, check it out. Now we're back to exponential times cosine again, right? So let me rewrite this last one just a little bit more suggestively. What we got here is 1/2 e to the 3x times sorry, just a moment of doubt there. Sine of 2x plus, oh fine, I won't try to simplify it. Sine 2x plus 3/4 rather, e to the 3x cosine 2x. And then multiplying this stuff, what do we get? 3 minuses, so I get minus 3 times 3 is 9. 4 downstairs, integral of e to the 3x cosine of 2x dx. If you tilt your head and squint, you can see that you had 4/4 of the integral to start with, right? So if you solve for the integral, what do you get? If I add that to the other side, I've got 13/4, right? So then that gives me 4/13 of 1/2 e to the 3x sine of 2x plus 3/4 e to the 3x cosine of 2x plus a constant. And there you go. Yeah.
Isn't this sine log x with the e to 3x cosine 2x is kind of like a similar problem
This is a similar problem
to this? Because
to that one?
if I substitute like u equals log s, the x problem. If I substitute u equals log x, is it like kind of like
Let me
it turns into like sine?
you want to let u equal log x. If you just forgive me, I'm going to make your u a beta. Okay, beta equals log x. Then you got yourself d beta equal dx over x. So we have integral sine of log of x dx is actually equal to integral of sine beta okay, so the dx is what?
Because beta is equal to log x, so x is equal to
So x is equal to e to beta. I see what you're doing. Just a second here. So dx is equal to x d beta, but that's equal to e to the beta d beta because beta equals log x tells me that x is equal to e to the beta. So this is really sine beta, e to the beta, d beta. Right. These are the same problems. Very good. That's why this phenomena happened again. Yeah. Very nice. So your point is you don't ever want to solve this problem again because you're just going to solve that problem and make the substitution? Or are you just pointing out that they're related? I like it. Very nice. Yeah, these are kind of, well, I mean, they're not kind of, they are very much related. Yeah. But I think most people won't see that relation directly. But anyway, integrate by parts twice, it loops back on itself. I mentioned that there was another method. Let me show you. So you asked, are there any easier ways to do certain ones of these problems? There is one trick I know for a certain kind of problem. I'll show you that now. So how about this? You had something like the integral of like x cubed e to the 2x dx. You should start to have a sense by now that you can solve this by integration by parts. What do?
Use x.
Right, you're going to say that's dv, this is 1, and this is u1, right? That's going to give you 1/2 x cubed e to the 2x minus 1/2 the integral of 3x squared e to the 2x dx, right? And then what are you going to do? Then you're going to integrate by parts. Again, right? Let's see here. I'll clean it up a little bit. What should I make my second? I should let this be du2, right? dv2 rather. This be my u2. What happens then? And then, let's see here. Let's see here, so I can, pull the hat, and then 2's cancel. So I'm just going to make this be my dv3, x will be my u3, and so I get 1/2 x e to the 2x plus the integral of 1/2 e to the 2x dx finally. And there's the answer, 1/2 x cubed e to the 2x minus 3/4 x squared e to the 2x minus 1/2 x e to the 2x plus 1/4 e to the 2x plus a constant. So that can happen to you, yes.
Just out of kind of more curiosity and help me grasp it a little bit better, what are some of the real world applications of this?
Excuse me. Well, for example, if you have something like a circuit with a sine wave, and something like a resistor and an inductor, something like that. Oh, wait a minute, you're asking about integration by parts. I don't know, the truth of the matter is the integration by parts is useful to do integrals, and integrals come up in all kinds of applications to all sorts of things. So, I don't know if I have a good answer for that I can give you in a minute here. I can show you a better way to do this, though. Like, what if you were to face something very similar? I don't know. You're like, not again, right? Let's use some common sense. Now that you have the experience of suffering through watching me do this, you kind of know where we're going, right? What's going to happen as you integrate by parts 3 times there? Yeah, you're going to get terms with x cubed. You're going to get terms with x squared, with x, without the x, and that's it, right? So in other words, you can already guess the format of your answer. It's ax cubed plus bx squared plus cx plus d, right? And all you really need to do is figure out the values of those constants, right? In other words, don't do the integration by parts. Know where the integration by parts is going and write down the guess in a convenient format and figure it out. Because that's way easier to actually say that it has to look like that and then differentiate. Differentiating both sides, what do I get? On this side, I get x cubed e to the minus x because that's what it means for it to be the antiderivative. Differentiate the antiderivative to get back to the integrand again, right? What happens on the other side, though? Product rule, right? So I got 3ax squared plus 2bx plus c times e to the minus x plus, well, minus ax cubed plus bx squared plus cx plus d times e to the minus x. And then you just group stuff. So like, let's see here, I've got a minus ax cubed e to the minus x, right? I've got a 3a minus b x squared e to the minus x. And 2b minus c times x e to the minus x. And then what else do I have? C minus d e to the minus x. And that's it, right? Oh, I'm sorry. I forgot to give you my standard response when someone asks me what the real-world application is. There's a very real-world application you should believe in because you believe that you exist, and you believe that you're taking the test in about 2 weeks. 3 weeks. I don't know. I guess it's 2 weeks now. There's a real-world application because you exist. Students don't usually appreciate this one that much, so I'm trying to reform myself and not give it so much. But it's always what I want to say. Anyway, so you may not have much experience with these kinds of equations, but this has to hold for all x, right? So what that means, actually, is that you can compare coefficients of like things. So, for example, I can read from this equation that because there's a 1 here, right, there has to be a 1 here. So what that tells me is that 1 is equal to minus a. So a is equal to minus 1. Yeah, I've done this before. And then I have met smart people. Don't confuse me with one. Let's see here. That is the coefficient of x squared e to the minus x. Where is the x squared e to the minus x? Over here. If you look really hard, you can see that there is 0 times x squared e to the minus x on the other side, right? So comparing that coefficient, we have 0 is equal to 3a minus b. And then we get 0 is equal to 2b minus c. And we get 0 is equal to c minus d. So you can solve these equations. You're like, I don't know how to solve 4 equations and 4 unknowns. It's so hard. Not really. These are easy. Let's see here. B is equal to 3a. It's minus 3. I don't know what that voice is. It's just a voice It's Kermit the Frog. Let's see here. C is equal to 2b. Minus 6 is equal to c, apparently. And d is equal to c. So what do we get? The integral of x cubed e to the minus x dx is equal to, what do we got? Minus x cubed minus 3x squared minus 6x minus 6 times e to the minus x plus a constant. There you go. Integration by parts without integration by parts. Yeah. Of course, if you understand it. Do you understand it?
When we integrate x cubed.
Where, I mean, I guess my question to you is where is this useful? It's it's only really useful if you can identify if you know where you're going, right? Like I suppose with something like this, you could know where you're going also, right? You kind of know it's going to be, I don't know, I mean, a little bit shakier. I mean, I guess I know that if I have e to the x cosine x dx, something like that, I kind of, after you work these a few times, you know you're going to have something like a e to the x cosine of x plus b e to the x sine x. This method starts to lose its, I mean, you still have to do product rules and, I don't know. There's a reason there's a reason your textbook isn't full of it. It's dangerous. The integration by parts method is straightforward and tedious, but successful. You guys have other questions about homework? Yes, no, me. What's that? Let's see here if I can find another one. How about the integral of x times x plus 5 to the 14th? Well, anyway, you guys can ask me more homework questions tomorrow, of course, also. Every day, really, for the most part. Number 17 and 8.2.
So are we kind of like doing homework on Tuesdays and Thursdays and classes on all the other days? Is that kind of how it works? Or?
We have class every day, but I'll try to take homework questions at the start of every day. So I think that's going to work for this semester. You know, I usually have time for about 10 minutes of homework, and then I can get into the lecture past that, something like that.
This is a lecture.
What's that?
This is a lecture. Wait.
I think so.
Oh.
Well, I mean, that's the thing that's beautiful about Calc 2 in part. Like, what do you have to lecture about integration by parts? The thing we did at the start, the UV, differentiating it, integrate both sides, that's it for the theory here. There's no more theory here. That will change later in the course. There's much more theory that goes with certain later sections, right? Some of you have been here before. You know it. You can attest to it. So,
Is that 5?
what's that?
Is that a 5?
That's a 5. There. Yeah, the 14. That's annoying, isn't it? So, I don't know if you really need integration by parts for this. Do you need integration by parts for this? Can't you just do u substitution? I'm going to do u substitution. This is u. So x plus 5 equals to u. So that means that x is equal to u minus 5. So this is the integral of u minus 5 times u to the 14th power du, which is the integral of u to the 15th minus 5u to the 14th du. So what you got is u to the 16th over 16 minus 5 over 15, aka 1/3, u to the 15th plus a constant final. Simplify it. 1/16 was u. X plus 5, yeah. Wow, this is kind of a... Yeah, I guess you could do this with integration by parts, but honestly, if I can do something with u substitution, by golly, I'm going to use u substitution. You know? So guys, I've decided as to not make you guys tired this semester. Tuesday and Thursday, we are ending about now. Is that agreeable?
Yeah.
All right. So there you go. That's your Calculus 2 for today. Now go do some homework.
You're wonderful.
This is a rather peculiar arrangement. I work less and you guys are happier.
I wouldn't say.
Tomorrow, integrals of trig functions galore. Oh, you can turn the video off if not already. You hit the button again.